All right, let's jump right into this explainer. Think about that landscaping project you're currently planning. You know, when we look at a beautiful, sturdy retaining wall, we naturally focus on the obvious stuff. The heavy stones, the neat interlocking blocks, maybe those massive boulders. We just think about all the earth it's holding back. But what if I told you the dirt isn't actually the main threat to your project? There's a silent, totally invisible enemy that causes way more structural failures than anything else. And to beat it, we've got to completely change how we think about what a retaining wall actually does.
So here's the absolute golden rule, the drainage first rule. I want you to keep this in mind for the rest of our time together. A retaining wall without drainage is essentially a dam waiting to burst. Look, dry soil is pretty stable, right? But when soil gets fully saturated with water, especially heavy clay soils, it becomes incredibly heavy and fluid. It literally stops acting like solid ground and starts acting like a slow-moving liquid. If your wall isn't designed to let all that water pass through, well, you've just built a dam, and you're setting yourself up for the ultimate danger of trapped water.
We've got a tight, highly structured blueprint for you today. We're going to cover the dam waiting to burst, gravity versus reinforced walls, the anatomy of a wall, our technical blueprint, and we'll wrap up with safety and compliance. Let's get to it. Okay, Section 1, the dam waiting to burst, hydrostatic pressure. We really need to start with the high stakes here, the absolute primary cause of catastrophic wall failure.
So, hydrostatic pressure. It's basically the intense force that water exerts as it builds up behind a structure. It adds massive extra weight and pushes laterally, meaning sideways, right up against your blocks. In clay-heavy soils, which love to hold moisture, this lateral pressure just keeps building and building until, honestly, the wall has absolutely no choice but to give way.
Now, if you're seeing any of these warning signs, red alert, your wall might already be experiencing active failure and you need to act fast. While vertical cracks usually just mean the ground is settling, horizontal cracking right at the mid-height of the wall, that is a massive red flag. It means the hydrostatic pressure is officially exceeding the structural capacity. And if the wall is bowing, or if your weep holes are completely bone dry right after a heavy rainstorm, well, you know your water is trapped. Moving on to Section 2, gravity versus reinforced walls, segmenting by function. Now that we fully respect our invisible enemy, let's look at the two primary ways we actually build these defenses.
We basically segment retaining walls by function, mostly based on how tall they need to be. On one side, we've got gravity walls. These are perfect for your lower heights, typically anything under 4 feet. They literally just use their own massive weight and a slight backward lean, which is called a batter, to hold back the earth. Now, on the other side, we have reinforced walls. When you need to go higher or support some heavy loads like a driveway, just stacking heavy blocks isn't going to cut it. You have to use synthetic geogrids or anchors to actually tie the face of the wall deep into the soil behind it. Looking directly at this, you can see exactly how a gravity wall leans back, resisting the earth through sheer bulk alone. But on the reinforced side, notice how it uses those horizontal geogrid ties. It stretches its strength deep into the hillside, effectively turning the native soil itself into part of the structural mass. It's just a brilliant piece of engineering. Which brings us to Section 3, Anatomy of a Retaining Wall. The section. The face of the wall is just the tip of the iceberg, right? So let's deconstruct what actually happens behind those visible blocks, layer by layer from the ground up.
This vertical cross-section right here shows how every single layer relies on the one below it to function. It's like a giant puzzle. Step 1 is the compacted base, the foundation. If this isn't rock solid, nothing else matters. Step 2 is your absolute lifeline, the drainage layer. This needs to be 12 to 14 inches of clean, crushed stone sitting directly behind the wall to let that water drop down harmlessly. Step 3 is your filter fabric. You wrap this between the native soil and your drainage stone to prevent all those tiny particles of dirt from washing into your gravel and clogging up the whole system. And finally, Step 4 is your backfill, which is just the native soil you put back into the excavation.
All right, Section 4, the technical building checklist, aggregates and compaction. We're getting into the strict rules for building your section right, starting with the exact materials you need.
Listen, you absolutely have to use angular crushed stone. No rounded river rock or pea gravel here. Why? Because those jagged angular edges physically lock together into a perfectly stable, unmoving matrix under pressure. Rounded gravel, it'll just shift and roll around like marbles, totally destabilizing your wall. Whether it's that 3/4 to 2-inch stone for your foundation base or the graded stone for your drainage zone, angular rock ensures water moves freely while the structure itself stays completely rigid. Now, this is huge. The lifts rule. This is one of the biggest mistakes we see, and it is entirely non-negotiable. You can never ever just dump a giant pile of backfill behind your wall. You must spread the soil and compact it in thin layers, called lifts, of 8 inches or less. Dumping soil without compacting it in lifts basically guarantees you're going to have future settling, sinkholes, and structural shifting. Definitely keep this checklist handy, guys, because poor leveling or skipping subsoil prep are the fastest ways to totally ruin your hard work. You've got to excavate down past the soft topsoil until you hit stable native earth. Then, your leveling has to be perfect. If that first base course is off by even a fraction of an inch, your entire wall will be crooked. Ensure the blocks naturally maintain their batter, and please, periodically check your weep holes to make sure that water is actually escaping.
Finally, Section 5, Safety, Codes, and Compliance. Before you even think about grabbing a shovel, we need to talk about the physical and legal limits of a DIY build.
3 to 4 feet. That's the magic number. If your project is creeping over 3 to 4 feet in height, depending on your local jurisdiction, you've generally crossed the threshold where a professional engineer's sign-off becomes a strict safety requirement. At that height, the sheer mass of the earth and that potential hydrostatic pressure we talked about, it gets so immense that guesswork is simply not acceptable. You've always got to check your local municipal regulations. Proper permits, soil tests, and inspections are literally required before you start moving earth. Approval must be obtained prior to proceeding, plain and simple. Think about it. If you build a beautiful 5-foot wall without a permit, the city can absolutely force you to tear the whole shebang down, no matter how great it looks.
So I want to leave you with this one critical thought before we wrap up this explainer. It brings us right back to where we started. Remember our drainage first rule? A retaining wall is just a dam unless you give the water an escape route. So ask yourself, where is the runoff actually going to go? Is the base perfectly level? Are you truly prepared to compact every single lift? If you can't confidently answer this central question about water, you aren't ready to build. But if you can, you are well on your way to building a structure that will stand strong for decades.